In this communication, I present some data concerning the interaction of nitric oxide on supported ruthenium. The ruthenium was prepared by impregnation of ruthenium carbonyl and time reduction at 350 degrees. This sample was previously characterized in our laboratory, for example, by CO interaction. And in this communication, I show some interesting phenomena concerning the nitric oxide absorption, reduction of nitric oxide, oxidation of ammonia formed by reduction, and reduction of nitric oxide by carbon monoxide. And some interesting phenomena of spillover and mainly of inverse spillover, as shown from Professor Budar in Budapest some days ago, are here shown. The ruthenium supported on titania is difficult to fully reduce. And CO absorption show that there are many species which are due to ruthenium oxidation. But a full reduction by absorption and interaction with CO can reduce very well, nearly well, the sample. The assignment is the usual assignment of ruthenium absorbed, CO absorbed on ruthenium. There are some species which are due to ruthenium-3 or ruthenium-2 interacting with 2 or 3 carbon monoxide. Professor Bell has shown that probably there are 3 species at least on the silica. But the ruthenium-2 phases is stabilized, strongly stabilized in the case of supported titania. Finally, the ruthenium-0 absorbed as usual at this frequency, which is usual as on monocrystal and 001 monocrystal. Okay? And the nitric oxide absorption show that the degree of the reduction of the sample can modify the spectrum absorbed nitric oxide. On fully oxidized sample, we have an absorption which can be assigned to ruthenium absorbed on absorbed on ruthenium-3 species. It is a very strongly absorbed species, and some complexes, homogeneous complexes of NO are exactly at the same frequency. Depending on the degree of the reduction of the sample, we obtain the following spectra. For example, for the sample reduced at 350 degrees centigrade, we have 2 bands at nearly 80 were numbered, which are assigned to ruthenium on NO on ruthenium-0, and another band at higher frequency which can be tentatively assigned to NO on ruthenium-2 species, which have been already shown to be present by NO. But what is more interesting is that increase in the temperature of reduction of the sample, we have the prevailing species ruthenium-0, but immediately we have an oxidation of ruthenium-0 species. And this is shown by the formation of large amount of nitrous oxide, which is probably formed also by the composition on the reduced titania phase, because the titania phase is nearly black in this condition of reduction, and become the transparency increases by absorption of NO. Therefore, an oxidation process with formation of intermediates and 2O species can be reflect in the advances. Then, on the oxidized species, I heat in oxygen no, I heat in hydrogen the oxidized ruthenium species, and there are the formation of ammonia, which can be assigned to ammonia absorbed on the titanium phase, which is stabilized. My sample contains only 1% of ruthenium. It's difficult to see if there are some species absorbed on ruthenium species. And this is shown also by isotopic experiment with deuterated ammonia. We have the formation of large amount of hydroxyl water and deuterated ammonia species. This is depending on the model of ammonia species shifted as usual by isotopic exchange. That the ammonia is absorbed on prevalent titanium phase is shown in this figure, which compares the absorption of ammonia on titanium, gases in the same conditions, on ruthenium titanium species, and the spectrum is exactly the same. Carbon monoxide showed that on titanium there are at least two sides of titanium 4 plus which can coordinate ammonia. And the two sides are shown by the two bands in which asymmetric bending mode is shifted. Ammonia is shifted. These modes are exactly at the same pressure. Only at 350 degrees we can have the decomposition of ammonia, and the bands decrease, or it's going to decrease because ammonia only at this frequency can be decomposed. The same occurs on oxidized species where a large amount of hydroxyl are formed because also a ruthenium oxidized phase is reduced. In this table, we resume the assignment of ammonia absorbed on the oxidized sample and reduced sample. That the more interesting mode of ammonia is the asymmetric bending mode. And I have not found a clear evidence of NH species which have been probably found by Bell and co-workers on my sample. Now, I show that absorbed ammonia can be oxidized at 300 degrees with formation of an NO species absorbed on the ruthenium, whereas there are some other bands which can be shown by experiment with isotopic sample, with isotopic compound, which can be assigned to nitrate species absorbed on titanium. You show here, for example, this band at 5081 number, which is shifted exactly for the isotopic experiment by nitrogen 15 nitrate, and which remain unchanging by reducing with deuterium. This is the assignment. What is intelligent, therefore? The oxidized nitric oxide is absorbed on ruthenium, And the nitrate, this nitrate, where are absorbed? The answer is that the nitrate are absorbed on the titanium. This is an experiment showing the oxidation of NO absorbed by oxygen, absorbed on the titanium treated in the same way. And we have exactly these marked, marked species are exactly at the same frequencies that I found on my sample. And is absent this band, but probably because the nitrate species are formed at high temperature, and this experiment carried out on my sample, ruthenium titanium sample, of oxidation at room temperature of NO show that are formed exactly the same bands found on the titanium alone. Probably there is here a band at the 150 wave number, which can be due to ruthenium nitrate, which is an ionic species and absorbed at lower frequency. Titanium nitrate is a covalent and easily volatile compound, which is formed and can be also easily decomposed on the sample. And if you heat, for example, under vacuum at 200 degrees, you see that the main bands disappear and remains only the bands which remain on our sample in the same condition of temperature. Now, I have a very nice experiment which can be interpreted, in my opinion, as an inverse spillover phenomenon. It's very clear, this is an occasional experiment. This is a sample, the number 1 curve, which is where ammonia is oxidized at 300 degrees. We have nitrate species, water, and NO species on routine. Then, if I dissolve at 200 degrees, the nitrate species and water fully dissolve, and the NO species on ruthenium increase. I have repeated this experiment, in this case with butyrated ammonia, because in order to eliminate this water band, which can be not and I obtained just the band of nitrate and water on shown, previously shown. Then, by outgassing, you see in this figure 2 that the nitrate band is decreases, strongly decreased, and NO bands probably on a ruthenium 2 species increase. This is a clear example of inverse spillover experiment from the sulfur to the ruthenium. And if this is increased also at 200 degrees centigrade, if I absorb NO, this experiment that the NO absorb again on this on the ruthenium sides, but the nitrate species are not formed at higher temperature. Okay. Okay, this is the first part of my talk. Then I have reduced it by CO absorbed NO, and I have found some isocyanated species. And the isocyanated species that are being studied from, for instance, imaging, some years ago, and it is clear, for example, platinum titanium, that the stability of isocyanate species depends strongly also on the support. For example, for platinum titanium, the isocyanate is easily formed but easily decomposed, more easily than on covalent platinum silica, because the higher ionic and electronic conductivity of the support easily decomposes the isocyanate species. And the frequency and the stability of the isocyanate decrease in the ore. And on titanium, platinum on titanium, the isocyanate is formed on the platinum and spills over the titanium, giving a band in this position. I have repeated some experiments on zinc oxide and on titanium, which are semiconductor and type super. And I have shown, for example, in the case of platinum on zinc oxide, that the stability of the isocyanate species depends on the reduction of the support. That is, the strong in weakly reduced support, which contains a minor amount of electron, of semiconducting electron, the isocyanate species is more stable and is formed and resist to until 300 degrees near. Whereas on the well-reduced compound support system, the isocyanate species is formed in lower quantities and is easily decomposed at lower temperature. This experiment has been reported in carried out on ruthenium titanium. I utilized carbon-13 because I have also followed by mass technique the product of format during the reaction. And on ruthenium, the isocyanate, there is a recent paper of Menzel and co-workers on ruthenium 001, which showed that isocyanate is formed at room temperature, giving a band in this position. But immediately at 50, 70 degrees centigrade, the species decomposes, and therefore it can be easily spill over on the support. I see that also depending on the sequence of absorption, before NO, 10 CO, we end on different amount of CO and NO present in the cell. We have a different reactivity and formation of isocyanate species. This is NO adsorbed, which is very not displaced or very weakly displaced by CO, also after a long time of contact. Only a weak amount of N2O is formed at room temperature. By heating at 150 degrees, is formed a small amount of isocyanate. All the isocyanate species at 2150 were numbered. And this corresponds exactly for carbon 12, carbon CO12 to 22 110 were numbered. Exactly as found on over titanium support metals. And the amount of isocyanate is very low. But I have in 10 minutes. It's very low, and it's decomposed immediately at 200 degrees. Of course, carbon dioxide and is easily formed, and only at higher temperature the ruthenium is reduced in the usual ruthenium CO, ruthenium 0 CO species. If the sequence of absorption is reversed, we observe that nitric oxide easily displaces carbon monoxide, and in this condition N2O species are formed in greater amount together with carbon dioxide, and then isocyanate species are not formed or formed in very low amount in this case. Finally, this can be followed also by mass experiments which show that this is the table, the sequence CO and NO follow the NO decomposition. When isocyanated species is nil, the formation of CO2 and nitrogen is favored, and this shows that the isocyanated species is a poison for the reaction of reduction or NO reduction. A conclusion. In this table, I show the frequency and the reactivity of isocyanated formed on different samples on platinum and ruthenium supported on titanium and zinc oxide. The trend is in full accord with the data of Solimosi. Only on the ruthenium zinc oxide we have a stability of isocyanated species, more stability. But in this case, the ruthenium is not well reduced, and because there is an electron transfer from zinc oxide to ruthenium, which lowers the electron conductivity of the support, and therefore the composition is more difficult. And the isocyanated are clearly absorbed on the support because the frequency is the same, and the stability of the isocyanate depends on the chemical nature of the absorbed side and the ionic conductivity of the support. Conclusions? The degree of reduction of the semiconductor supports influences the stability of the isocyanates, which are more easily decomposed on more strongly reduced samples, therefore for an increasing electronic conductivity. The sequence of absorption is very important because if, for example, on ruthenium and NO absorb on ruthenium, it is more difficult to dissociate NO itself, and the formation of isocyanate is more difficult. The ratio CO and NO is also very important. If CO prevails, the formation of isocyanate is favored. If NO prevails, N2O, nitrogen, and carbon dioxide are favored. For ruthenium, the NO absorption is strongly absorbed the ruthenium NO species hinders the NO dissociation and also the formation of isocyanates. When nitric oxide is displaced by CO, the ruthenium is reduced to ruthenium 0, therefore dissociate NO with formation of isocyanates both on ruthenium titanium and on ruthenium zinc oxide. Thank you for listening.
Papers now for discussion. Please.
Ricardo Parra from Inter Venezuela. So I have a short question. When you make the NO insertion, did you observe some modifications, time position, or the head of the peaks of NO absorbed form
ruthenium.
As a function of the time.
On titania,
The time of the time.
the time. The time era nearly immediate, recorded after a few minutes. They are recorded after a few minutes. The absorption is absorbed, and then it is absorbed at two different pressures, and there is also desorbed nearly immediately. It is a quick reaction which occurs on ruthenium 0. NO is easily dissociated, can be easily dissociated also. And the N2O formation shows that depending on the degree of reduction of the sample, we have a very easy process of dissociation.
You showed the formation of N2O in several instances. This can be done in different ways, either by dissociation of the NO on metallic ruthenium, or also via dinitrosis. Do you have evidence for dinitrosis?
No, I have not at all evidence of dinitrosis species in this case. You can have a contribute of the support, because if you absorb NO on titania alone reduced at high temperature, we observe the increase of the transparencies of the structure. This shows that oxygen is, nitric oxide is decomposed, oxygen partially restore the stoichiometry of titania, and but I don't found NO absorption on the surface. And I have not found, at least at room temperature, at higher temperature, NO absorption as a dynamic species.
You had a transparency showing isocyanate formation on a well-reduced ruthenium titania and not so well-reduced ruthenium titania. Isocyanate formation, well. If I remember well, on a well-reduced ruthenium titania, there was practically no isocyanate, but a well-intense carbon dioxide that appeared on the spectra.
Yes.
The situation on not so well-reduced sample, the situation was reversed. There was a big isocyanate band. There was practically no CO2 on the spectra.
But
So could you comment?
it is not
Because
exact.
I have the feeling a little contradiction.
It is not exactly so. The results are not exactly read. Because seems to me that carbon dioxide is present always in this amount. The mass data shows that carbon dioxide is formed in there is a different ratio, but carbon dioxide is here always formed.
You had another transparency because it is of two parts. The upper part showing the well-reduced ruthenium titania, the bottom part
It's
showing
not on-
not so well.
No, it's probably, no, sorry. No, I'm not. I'm only. It's a platinum, but platinum, here there is not.
Yes.
No, this is not dioxide. Dioxide is, okay. This is, okay. This, yes. In this case, well, this is in accord with my hypothesis, because on strongly reduced sample, isocyanate species is formed with, is easily decomposed. It's formed and easily decomposed, and then carbon dioxide is formed in greater amount. And this is shown that when isocyanate species is present in larger amount, carbon dioxide is formed with more difficult.
I hate to cut off the discussion